This is part 3 of the lecture on the properties of the Z-transform. In this lecture, I want to talk about upsampling, differentiation, and convolution, and an application to linear time invariant systems. We start with the upsampling properties. So suppose we have a signal x of n, a discrete time signal. We say that the upsampled signal with upsampling factor 3, for example, is the following signal here, where you introduce k minus 1, meaning 2 zeros between each two signals. So one thing to keep in mind here is that k is equal to the number of zeros you introduce plus 1. So k here is the number of intervals, extra intervals you're creating between two impulses of the original signal. So that's why k equal to 3. That's just the notation. And we denote the upsampled signal with upsampling factor k. We denote it by x subscript k. And this would be the upsampled version of x of n with upsampling factor k. And like I said, so it's obtained by inserting k minus 1 zeros between two successive values of x of n, and the zeros are added at equal intervals between the two signals, as you can see here. And in a formal way, this is how we write it. So xk of n is equal to the original signal at n by k, because here we multiplied the times by k. And otherwise, it's equal to 0. So if you're a little bit confused about this notation, I suggest you take an example and you check. You can work it on this example. You can check that if you apply this formula to this signal, you get exactly what we want, meaning by introducing k minus 1 zeros between two impulses of x of n. And of course, the question here, what is the Z-transform of the upsampled signal? To answer this question, let us take a small example. So let's take a signal which is the following. So it's at 0 is equal to, say, 1, and at 1 is equal to, let's say, 2. So this is x of n, and x of z here is going to be equal to 1 plus 2z minus 1, right? Now, if I pick the upsampled signal with k equal to 2, so I'm going to get at 0, I'm going to have 1, and I'm going to have at 1, I'm going to have 0, and at 2, 0, and then at 3, I would have 2 here. So this is x2 of n. Again, so I'm following the notation x2 of n, meaning I'm upsampling with an upsampling factor 2. Now, if I find, let's call this y of n, just to make it easy to refer to the Z-transform. So here, y of z is going to be equal to, if I just apply the definition, so it's going to be equal to 1 plus, and now the value of the signal 2 is at n equal to 3, so it's going to be equal to 2z minus 3. And so the one way to see it here, so if we had another pulse here, let's say at 2, let's suppose it's 10, right here I would have plus 10z minus 2, and here I would have to have plus, if you do, so you're going to have 3, 4, 5, and 6, you're going to have 10 here. So plus 10z minus 6 also. So what does that mean? So you can check that y of z is actually equal to x of z cube here, because, so this is cube, so let me erase it. So x of z cube, and then to see why this is true, you can check here that so whatever power of z that was 1, it became, or negative 1, it became negative 3. And whatever was at n minus 2, it became the same signal or the same impulse, but at z equal to 6. So I'm always multiplying by 3, and this is how I get the formula. And in the next slide, I will give the general formula here. And this is the general formula that gives me the upsampled signal, the z transform of the upsampled signal as a function of the original signal. So the upsampled signal has a z transform equal to x evaluated at z to the power k. And usually we have the following kind of diagram that denotes x of the upsampling operation. So here x of n has x of z, and then you have upsampling with an upsampling factor k, and then y of z, which is the z transform of the upsampled signal, is equal to x evaluated at z to the power k. And the same thing, so here the ROC is equal to ROC where z is replaced by z to the power 1 over k. So you just replace in the equation of the ROC, you replace z by z to the power 1 over k. For example, let's suppose that the ROC was z greater than a, and in the xz of k, the ROC is going to become the norm of z of k is greater than a. This means that the norm of z is greater than a 1 over k. So that's what's going on. The seventh property is the property on what we refer to as differentiation, and it says the following, that the z transform of a signal that is n x of n is actually minus z, the derivative of x of z with respect to z. And here I have the proof. It just follows from the definition. And the ROC is still the same. Maybe a small example will clarify what's going on. So we know that if I have, let's suppose x of n is equal to, let's say, that's the example I've been running with, 1 over 2 to the n u of n, then I know that x of z is going to be equal to z divided by z minus 1/2 with z greater than 1/2, right? Now the question is, suppose let's take y of n to be equal to n by 2 to the n u of n. And now find y of z. And you can see here that if you apply the differentiation property, then you know that y of z is going to be equal to minus z, the derivation with respect to z of z divided by z minus 1/2. And then you can do the calculation here, and then the ROC will remain the same here. Okay, so this is a formula that can be very useful if you can spot that the signal that you're trying to find is n times something you already know. And the last property we're going to talk about, and it's actually property 8, I think. So there's a typo. I'll fix it in the slides. It's maybe the most important property, which you've seen before and probably in the Laplace lectures. And you're going to see a lot in different courses, which is convolution. So we know that the z transform of the convolution is the product of the z transform. So again, this is super important, that when you convolve two signals, what you do, the convolution in the time domain is equivalent to simple product in the z domain. And this makes things easier, and this motivates us to work in the z domain, because the output of an LTI system is the convolution of two signals. And then when we work in the z domain, which is equivalent to the frequency domain, instead of convolution, which is a little bit complicated, you have just simple multiplication. And in terms of the ROC, we need the ROC of both signals. We need both signals to converge, so the ROC is the intersection. And here I try to represent what I just said in terms of figures. So in the z domain, if you have an LTI system with an impulse response that is h of n, so this is called the impulse response, just to remind you. Then the output of the signal is y of n, which is the convolution of x with the impulse response. And in the z domain, if the input has z transform x of z, then the output has a z transform y of z, which is h of z times x of z. Where, sorry, here there's also a typo, so this is supposed to be h of z here. So this thing here is h of z. And we call h of z the transfer function of the system. So this is an important concept, and I'll think we will revisit it again with some examples. Okay, so h of z, the transfer function of a system, which is the z transform of the impulse function, determines how the system is going to behave when you input to it a signal, a certain signal x of n. And the output is going to be given by the following equation. So in fact, the output y of z is equal to h of z times x of z. And now you do z inverse, and you find x of y of n. Let us work out an example. So the question here is, consider the following linear time invariant system with the following difference equation. And the question is to find its transfer function. So to find its transfer function, we need to find, so the transfer function, meaning what's asked, is to find h of z, which is y of z divided by x of z. So what I can do, I can take the z transform of this equation that ties together the input and the output, and I can find that here, if I do the z transform on the right or on the left, so if I do z here of this is going to be equal to the z transform of this, and then I can use linearity, right? So I know that this is y. So the question here, so what is the z transform of yn minus 1? So the z transform of yn minus 1 is, this is a shifted version, so it's going to be equal to z minus 1 times y of z plus y of z. So here I used both linearity and the shift property is equal to 2x of z minus 3 z minus 1 x of z plus 1/2 z minus 2 x of z. And now I can write that 1 plus z minus 1 y of z is equal to 2 minus 3z minus 1 plus 1/2, here should be minus 2, plus 1/2 z to the power minus 2 x of z. And then I can write y of z divided by x of z equal to 2 minus 3z minus 1 plus 1/2 z minus 2, 1 plus z minus 1. And this is the transfer function of the system. So here I did the calculations again, and if the question is to find the impulse response, so here I could add, let's say, find h of n, which is the impulse response. Then you have to find z inverse here. And we talked about this. So you're going to have to do partial fraction expansion and then invert each part of the fraction. And this brings me to the last slide in this series of lectures. And my goodbye gift to you is the following exercise, which is to find the transfer function and the impulse response. So I need both of these things of the causal LTI system given by the following difference equation.